An LLM is a type of AI designed to understand and generate human-like text by predicting the next word in a sequence. For example, if you type, "all that glitters," it will predict, "is not gold." This is relevant because LLMs are the foundation for popular AI tools like chatbots and content creators, forming the core technology that processes and responds to our text queries. Tokenization is the process of breaking down a sentence into smaller, meaningful pieces called tokens. Instead of just splitting by words, it might separate a word like glitters into glitter and ers to better understand its meaning. This is important because it's the first step for an AI to truly understand human language, allowing it to analyze grammar and context more effectively. Vectors are numerical representations, like coordinates on a map, that capture the meaning of a token. Words with similar meanings, like apple and banana, are placed close to each other in this meaning map, while words with opposite meanings are far apart. This concept is key because it allows AI models to understand the relationships and semantic similarities between words, which is essential for constructing coherent sentences. Attention is a mechanism that helps an AI understand context by focusing on nearby words to determine the correct meaning of an ambiguous word. For example, it helps the model know that apple, in tasty apple, refers to a fruit, while in Apple's revenue, it refers to the company. This is a breakthrough concept that allows AIs to grasp contextual meaning, leading to much higher quality and human-like responses. This is a training method where the AI learns from data without needing humans to label it first. The AI creates its own learning exercises, like predicting a missing word in a sentence or a hidden patch in an image. This is highly relevant because it makes training AI models much cheaper and more scalable, as it can learn from the vast amount of unlabeled data available on the internet. A transformer is the specific architecture or engine inside most modern LLMs that predicts the next word. It uses multiple layers of attention and other components to process input text, understand complex relationships like sarcasm, and generate a final output. This is the core technology that made today's powerful LLMs possible, although new architectures could potentially replace it in the future. Fine-tuning is the process of taking a general-purpose AI model and further training it on specific data to specialize in a certain task or domain, like medicine or finance. This helps the model provide more accurate and relevant answers for that specific field. This is important because it allows a single base model to be adapted for many different, specialized applications, from customer service to medical diagnosis. This technique involves giving the AI a few examples of how to answer a question right before asking the actual question. By providing examples within the prompt, you guide the model on the desired format and style of the response. This is a simple yet effective way to improve the quality and accuracy of the AI's answers during real-time use, without needing to retrain the model. RAG is a technique where the AI retrieves relevant, up-to-date documents or data from an external source, like a company's policy documents, and uses that information to answer a query. This provides the model with specific context it wasn't originally trained on. This is crucial for making AI responses more accurate and factually grounded, especially for company-specific information or recent events. A vector database is a specialized storage system designed to efficiently store and search for vectors. When a user asks a question, the system converts the query into a vector and quickly finds the most similar, and therefore most relevant, documents in the database. This technology is the backbone of RAG, enabling fast and effective retrieval of contextual information needed to generate high-quality answers. MCP is a standard way for an AI to connect with and use external tools and services, like airline booking systems. This allows the model not just to find information but also to perform actions, such as booking a flight on the user's behalf. This protocol makes ICE more powerful and capable by enabling them to interact with the real world and execute complex tasks beyond just generating text. Context engineering is the overall practice of providing an AI with all the necessary information, context, to generate the best possible response. It combines techniques like few-shot prompting, RAG, and MCP. This is a key discipline for AI engineers because it focuses on optimizing the information flow to the AI, making it more aware of chat history, user preferences, and external data to deliver stateful, personalized interactions. An AI agent is a long-running, autonomous program that can use an LLM, query external systems, and even communicate with other agents to achieve a goal. For example, A travel agent could monitor flight prices and automatically book a trip for you when it finds a good deal based on your preferences. Agents represent the future of AI, moving from simple question answering to proactive, goal-oriented systems that can manage complex tasks for us. RLHF is a training method where humans rate the AI's responses, e.g., thumbs up or thumbs down. The AI learns from this feedback, trying to generate more responses that get positive ratings and fewer that get negative ones, much like a dog learning a trick for a treat. This technique is extremely powerful for aligning AI behavior with human preferences, making models more helpful, harmless, and generally better to interact with. Chain of thought is a technique where the AI is prompted to think, step by step to solve a problem, rather than just giving a direct answer. By breaking down its reasoning process, the model can tackle more complex problems and arrive at a more accurate solution. This is significant because it enhances the AI's reasoning abilities, making it more transparent and reliable for tasks that require logical deduction. Reasoning models are AIs specifically designed to solve problems by figuring out the steps needed to reach a solution, often using techniques like chain of thought. These models can dynamically adjust the number of reasoning steps they take depending on the problem's difficulty. This represents a major advancement in AI, moving beyond simple pattern matching to more sophisticated problem-solving capabilities. Multimodal models are AIs that can understand and generate information in multiple formats beyond just text, such as images and videos. For example, they can analyze a photo and tell you what's in it or create a new image from a text description. This is relevant because combining different data types gives the AI a deeper understanding of the world, leading to better performance and opening up new applications in media creation and analysis. SLMs are smaller, more specialized versions of LLMs with fewer parameters. While less broadly capable than giant LLMs, they can be trained on company-specific data to become experts in a particular task, like sales or customer service. They are important for businesses seeking more control, data privacy, and cost-effective AI solutions for specific use cases. Distillation is the process of creating a small language model, SLM. It involves using a large, powerful, teacher model to train a smaller, student model. The student model learns to mimic the teacher's outputs, effectively compressing the teacher's knowledge into a more efficient form. This is a key technique for developing cost-effective and faster SLMs that can be easily deployed for specific tasks.
Quantization is a technique used to make a trained AI model smaller and faster by reducing the precision of its internal numbers, weights, for example, from 32-bit to 8-bit numbers. This process reduces the model's memory footprint and speeds up its response time during use. This is an important optimization step that lowers the cost of running AI models in production, making them more accessible and efficient. Supervised learning is a training method where the AI learns from labeled examples, like a student learning from a textbook with answers. For instance, showing the model thousands of labeled photos of cats and dogs teaches it to distinguish between them. This is fundamental because it's one of the most reliable ways to train AI for specific classification and prediction tasks, providing clear targets for the model to learn from. Unsupervised learning is when an AI discovers patterns and structures in data without being told what to look for. Like sorting a box of mixed items into piles based on similarity, the AI groups similar data points together on its own. This is valuable because it can uncover hidden insights and patterns in data that humans might not have anticipated, making it essential for exploratory data analysis and clustering. Transfer learning is the practice of taking knowledge learned from one task and applying it to a different but related task. Like how learning to play guitar helps you learn bass faster, a model trained on general images can be fine-tuned for medical imaging. This dramatically reduces training time and data requirements, making AI development more efficient and accessible for specialized domains. Pre-training is the initial phase where an AI model learns general knowledge from massive amounts of data before being specialized for specific tasks. Think of it as getting a broad education before choosing a career specialization. This is crucial because it gives models a foundational understanding of language or vision, which can then be efficiently adapted to countless specific applications. Overfitting occurs when an AI model memorizes its training data too well, including noise and outliers, making it perform poorly on new, unseen data. It's like a student who memorizes textbook examples but can't solve similar problems with different numbers. Understanding overfitting is critical for building AI systems that generalize well to real-world scenarios, ensuring reliability beyond the training environment. Underfitting happens when an AI model is too simple to capture the underlying patterns in the data, resulting in poor performance on both training and test data. Like trying to fit a straight line to data that curves, the model lacks the complexity needed. Recognizing underfitting helps developers know when to increase model capacity, ensuring the AI is sophisticated enough for the task at hand. Regularization is a set of techniques used to prevent overfitting by adding constraints that discourage the model from becoming too complex. Like adding rules to keep a solution elegant rather than unnecessarily complicated, regularization keeps models generalizable. This is essential for building robust AI systems that perform consistently on new data without memorizing training examples. An epoch is one complete pass through the entire training dataset during the learning process. If you have 1,000 images and the model looks at all of them once, that's one epoch. Training typically involves many epochs. Understanding epochs is important for monitoring training progress and knowing when a model has learned enough, preventing both undertraining and overtraining. Batch size refers to the number of training examples the model processes before updating its internal parameters. Like grading 10 student papers before adjusting your grading rubric versus grading all 100 first, different batch sizes affect learning efficiency and stability. This parameter significantly impacts training speed, memory usage, and model performance, making it a key consideration in AI development.
Learning rate controls how quickly an AI model updates its knowledge based on errors it makes. A high learning rate means big adjustments, fast but potentially unstable learning, while a low rate means small, careful adjustments, slow but stable. This is one of the most critical hyperparameters in AI training, as the wrong learning rate can cause training to fail or take unnecessarily long. Gradient descent is the fundamental optimization algorithm that helps AI models learn by iteratively adjusting parameters to minimize errors. Like walking downhill in fog by always stepping in the steepest downward direction, the model finds better solutions step by step. This is the mathematical engine that powers most AI learning, making it possible for models to improve their performance systematically. Backpropagation is the method by which an AI model figures out which of its internal parameters caused errors and needs adjustment. Like tracing backward through a chain of decisions to find where things went wrong, it calculates how much each parameter contributed to mistakes. This breakthrough algorithm is what makes training deep neural networks possible, enabling models to learn complex patterns across many layers. A loss function is a mathematical formula that measures how wrong an AI model's predictions are compared to the correct answers. Like a scorecard showing how far off target each attempt was, it quantifies the model's mistakes. This is crucial because it gives the model a clear objective to optimize, guiding the learning process toward better performance. Data augmentation is the technique of artificially expanding training data by creating modified versions of existing examples. Like training a face recognition system with photos rotated, zoomed, or color adjusted, it helps the model see more variations. This is important because it improves model robustness and reduces overfitting, especially when original training data is limited. Active learning is a strategy where the AI identifies which new examples would be most valuable to learn from and requests human labeling specifically for those cases. Instead of randomly labeling data, it focuses effort on the most informative examples. This dramatically reduces the amount of labeled data needed, making AI development more efficient and cost-effective. A neural network is a computing system inspired by biological brains, consisting of interconnected nodes, neurons, organized in layers that process information. Like how our brain's neurons fire in patterns to recognize faces or solve problems, artificial neurons activate to process data. This is the fundamental building block of modern AI, providing the architecture that enables machines to learn complex patterns. Deep learning refers to neural networks with many layers, deep architectures, that can learn hierarchical representations of data. Like learning to recognize faces by first detecting edges, then features, then full faces, each layer builds on the previous one. This approach has revolutionized AI by enabling automatic feature learning, eliminating the need for manual feature engineering. A CNN is a specialized neural network designed for processing grid-like data such as images. It uses filters that slide across the image to detect patterns like edges, textures, and eventually complex objects. This architecture is fundamental to computer vision, powering applications from photo tagging to medical image analysis. An RNN is a neural network designed to process sequential data by maintaining a memory of previous inputs. Like reading a sentence word by word while remembering what came before, RNNs process sequences with context. This architecture was crucial for early language models and time series prediction, though transformers have largely replaced them for language tasks.
LSTM is an advanced type of RNN that can remember information over longer sequences by using special memory cells and gates. Like taking notes while reading a long document to remember key points, LSTMs selectively retain important information. This solved the vanishing gradient problem in RNNs, making it possible to learn from longer sequences effectively. This is a two-part neural network design where the encoder compresses input into a meaningful representation, and the decoder generates output from that representation. Like how a translator first understands a sentence in one language then produces it in another, this architecture handles transformation tasks. This is fundamental to machine translation, summarization, and many sequence-to-sequence tasks. Residual connections are shortcuts in neural networks that allow information to skip layers, making it easier to train very deep networks. Like taking an express elevator that skips floors versus stopping at each one, information can flow more directly. This innovation enabled the training of networks with hundreds of layers, dramatically improving performance on complex tasks. Beyond basic attention, advanced attention mechanisms allow models to focus on different parts of input simultaneously with varying importance weights. Like a conductor directing different sections of an orchestra, the model orchestrates which information to emphasize at each step. This flexible focusing ability is key to handling complex relationships in data, enabling sophisticated understanding and generation. Self-attention is when a model compares each element in a sequence with all other elements to understand relationships within the same input. Like considering how each word in a sentence relates to every other word to grasp the full meaning, this creates rich contextual understanding. This is the core mechanism in transformers, enabling them to capture long-range dependencies efficiently. Positional encoding adds information about the position of tokens in a sequence to the model, since transformers don't inherently understand order. Like adding page numbers to shuffled book pages so you can reassemble the story, this preserves sequence information. This is essential for transformers to understand word order and sentence structure, maintaining the meaning that depends on sequence. An embedding layer converts discrete tokens, like words, into dense vectors that capture semantic meaning. Like translating words into coordinates on a meaning map, it creates a mathematical representation the model can process. This is the bridge between human language and mathematical computation, enabling AI to work with text numerically. Dropout is a regularization technique where random neurons are temporarily turned off during training, forcing the network to learn more robust features. Like practicing a sport with different teammates each time so you don't rely on specific people, the model learns to be more resilient. This prevents overfitting and improves generalization, making models more reliable on new data. Normalization layers standardize the inputs to each layer during training, making the learning process more stable and efficient. Like adjusting the volume levels of different audio tracks so they blend well, normalization ensures consistent signal strength. This accelerates training and improves model performance, making it easier to train deep networks successfully. Activation functions introduce nonlinearity into neural networks, determining whether and how strongly a neuron should activate based on its inputs. Like deciding whether evidence is strong enough to trigger an alarm, activations control information flow. These are crucial for enabling neural networks to learn complex, nonlinear patterns, without which they could only model simple linear relationships.
Skip connections are pathways that allow information to bypass one or more layers in a neural network, similar to residual connections. Like having both local roads and highways in a city for different types of traffic, these provide flexible information flow. They improve gradient flow during training and help preserve important information, making networks both deeper and more trainable. Generative AI refers to models that can create new content, text, images, music, code rather than just analyzing or classifying existing content. Like an artist creating original paintings rather than just identifying art styles, these models produce novel outputs. This represents a paradigm shift in AI capabilities, moving from perception to creation and opening entirely new applications. Diffusion models generate images by starting with random noise and gradually refining it into a coherent image through learned denoising steps. Like sculpting by gradually removing noise to reveal a form, these models iteratively improve quality. This approach has achieved state-of-the-art results in image generation, powering tools like DALL-E and Stable Diffusion. A GAN consists of two competing neural networks, a generator that creates fake data and a discriminator that tries to distinguish real from fake. Like an art forger and art detective improving together, both networks get better through competition. This adversarial training produces remarkably realistic synthetic data, though diffusion models have recently surpassed GANs in some domains. A VAE is a generative model that learns to compress data into a compact representation and then reconstruct it, with the ability to generate new samples by sampling from the learned space. Like learning the essence of faces and then creating new faces with those essential features, VAEs capture data distributions. This enables controlled generation and interpolation between examples, useful for creative applications and data synthesis. Temperature is a parameter that controls the randomness of AI text generation. Low temperature makes output more predictable and focused, while high temperature makes it more creative and diverse. Like adjusting how adventurous versus safe you want recipe variations to be, temperature balances coherence and creativity. This is crucial for controlling the style and creativity of generated content, allowing users to tune outputs for their specific needs. Top K sampling is a generation strategy where the AI only considers the K most likely next tokens when generating text. Like a chef choosing only from the top 10 ingredients for a dish rather than considering all possibilities, this balances quality and diversity. This technique improves generation quality by preventing the selection of very unlikely tokens, while still maintaining some creative variability. Top P sampling considers tokens until their cumulative probability reaches P, dynamically adjusting how many options to consider based on confidence distribution. Like adjusting your consideration set based on how clear the best options are, this adapts to context. This produces more natural and contextually appropriate generation than fixed K sampling, improving text quality across diverse situations. Beam search is a generation strategy that explores multiple possible sequences simultaneously, keeping track of the most promising options at each step. Like planning a route by exploring several paths and keeping the best ones, it finds high-quality complete sequences. This is especially useful for tasks requiring optimal outputs like machine translation, where the best overall sequence matters more than individual word choices. Prompt engineering is the practice of carefully crafting input prompts to get desired outputs from AI models. Like knowing the right questions to ask an expert to get useful answers, effective prompts guide model behavior. This has emerged as a critical skill for working with LLMs, as the same model can produce vastly different results based on how you ask. Zero-shot learning is when an AI performs a task it was never explicitly trained on, relying solely on its general knowledge and the task description. Like a chef cooking a dish from a cuisine they've never made before using general cooking knowledge, the model adapts without specific examples. This demonstrates true generalization capability, making models more flexible and reducing the need for task-specific training. One-shot learning is when an AI learns to perform a task from just a single example. Like learning a new card game by watching one hand being played, the model generalizes from minimal data. This is valuable for tasks where gathering many examples is difficult or expensive, enabling rapid adaptation to new scenarios. Instruction tuning is a training method where models learn to follow diverse natural language instructions across many tasks. Like training a personal assistant to understand various commands, this makes models more controllable and useful. This is key to making LLMs helpful and user-friendly, enabling them to understand and execute user intentions reliably. Constitutional AI is an approach where models are trained to follow specific principles or rules, defined as a constitution, making their behavior more predictable and aligned with human values. Like teaching ethics through a code of conduct, models learn boundaries and guidelines. This is crucial for AI safety and alignment, helping ensure models behave responsibly even in novel situations. Prompt chaining is breaking down complex tasks into a sequence of simpler prompts, where each output feeds into the next prompt. Like solving a complex math problem by breaking it into steps, this manages complexity systematically. This technique enables AI to handle more sophisticated workflows, effectively extending capabilities beyond single prompt limitations. Negative prompting explicitly tells the AI what not to include in generated content, particularly useful in image generation. Like giving a chef a list of ingredients to avoid along with a recipe, this refines outputs by exclusion. This provides finer control over generation, helping users avoid unwanted elements and improve output quality. A benchmark is a standardized test or dataset used to evaluate and compare AI model performance. Like using SAT scores to compare students, benchmarks provide objective performance metrics. This is essential for measuring progress in AI research and helping practitioners choose appropriate models for their needs. Perplexity measures how well a language model predicts text, with lower perplexity indicating better prediction. Like measuring how surprised you are by each word in a sentence, it quantifies predictability. This is a key metric for evaluating language models, though it doesn't always correlate perfectly with human perceived quality. Blue score measures the quality of machine-generated text by comparing it to human reference texts, commonly used for translation. Like checking how many phrases match between a student's translation and a teacher's model answer, it quantifies similarity. This provides an automated way to evaluate generation quality, though it has limitations in capturing meaning and fluency. F1 score is a metric that balances precision, accuracy of positive predictions, and recall, coverage of actual positives, giving a single performance measure. Like judging a test by both how many correct answers you gave and how many you didn't miss, it considers both accuracy and completeness. This is crucial for evaluating classification tasks, especially when dealing with imbalanced datasets. A confusion matrix is a table showing an AI classifier's predictions versus actual labels, revealing patterns in correct and incorrect classifications. Like a detailed scorecard showing not just wrong answers but what you confused them with, it provides diagnostic insight. This helps identify specific weaknesses in models, guiding improvements and understanding failure modes. Precision measures what percentage of positive predictions were correct, while recall measures what percentage of actual positives were found. Like evaluating a spam filter by both false alarms, precision, and missed spam, recall, these metrics capture different aspects of performance. Understanding this trade-off is essential for tuning models to specific application requirements, as you often must balance between them. The ROC, receiver operating characteristic, curve plots a classifier's true positive rate against false positive rate at various thresholds. Like visualizing how alarm sensitivity affects both catches and false alarms, it shows performance across all possible operating points. This is valuable for choosing the right threshold for your application, balancing different types of errors based on their costs. Cross-validation is a technique for evaluating model performance by training and testing on different subsets of data multiple times. Like testing a student's knowledge with multiple different exams rather than just one, this gives a more reliable performance estimate. This prevents overfitting to a single test set and provides confidence in how well the model generalizes. A/B testing involves comparing two versions of an AI model or feature by randomly assigning users to each version and measuring outcomes. Like testing two store layouts by seeing which produces more sales, this provides real-world performance data. This is critical for validating AI improvements in production, ensuring changes actually benefit users. An ablation study systematically removes components from a model to understand their individual contributions. Like removing ingredients from a recipe one at a time to see what each adds, this reveals which elements matter most. This is essential for understanding model behavior and identifying which architectural choices or training techniques drive performance. Model serving is the infrastructure and process of making a trained AI model available for real-time predictions in production. Like setting up a restaurant kitchen to serve customers after developing recipes, this bridges development and deployment. This is crucial for moving AI from research to real-world applications, requiring considerations of latency, throughput, and reliability. An API is a standardized way for applications to interact with AI models, defining how to send requests and receive responses. Like a restaurant menu that tells you how to order food, an API specifies how to use a service. This enables easy integration of AI capabilities into applications, making powerful models accessible to developers without AI expertise. Latency is the time delay between sending a request to an AI model and receiving its response. Like the wait time at a drive-thru, lower latency means faster service. This is critical for user experience in real-time applications, where delays can make AI systems feel unresponsive or unusable. Throughput measures how many requests an AI system can process in a given time period. Like how many customers a restaurant can serve per hour, this determines system capacity. This is essential for scaling AI to many users, affecting infrastructure costs and service quality under load. Model compression encompasses techniques to reduce model size and computational requirements while maintaining performance, including quantization, pruning, and distillation. Like compressing a file to fit on a USB drive without losing important data, this makes models more deployable. This is vital for running AI on resource-constrained devices like smartphones and edge devices. Edge computing runs AI models on local devices, phones, IoT devices, rather than in the cloud, processing data where it's generated. Like having a calculator in your pocket versus calling someone to do math for you, this reduces latency and protects privacy. This enables AI in offline scenarios and reduces dependence on internet connectivity, crucial for many real-world applications. Model monitoring tracks AI system performance in production, watching for degradation, errors, or unexpected behavior. Like regularly checking a car's dashboard while driving, this ensures ongoing reliable operation. This is critical because model performance can degrade over time as real-world data drifts from training data, requiring intervention. Data drift occurs when the statistical properties of input data in production differ from training data, potentially degrading model performance. Like a weather forecasting model trained on summer data failing in winter, changed conditions challenge the model. Detecting and addressing drift is essential for maintaining AI reliability, requiring continuous monitoring and potential retraining. Model versioning systematically tracks different versions of AI models, their training data, and configurations, enabling reproducibility and rollback. Like keeping numbered drafts of a document, this maintains a clear history. This is crucial for production AI systems, allowing teams to manage updates, compare performance, and revert problematic changes. Shadow deployment runs a new model version alongside the current production model, comparing their outputs without affecting users. Like having an understudy perform alongside the main actor without the audience seeing, this tests in real conditions safely. This reduces risk when deploying model updates, catching issues before they impact users. Characteristics like race, gender, or age, often due to biased training data. Like a biased hiring manager who unfairly favors certain candidates, biased models perpetuate discrimination. Addressing bias is critical for ethical AI deployment, requiring careful data curation, evaluation, and mitigation strategies. Fairness metrics quantify whether an AI system treats different groups equitably, measuring outcomes across demographic categories. Like checking if a grading system produces similar score distributions for different student populations, these assess equity. These metrics are essential for identifying and addressing discrimination, though defining fairness itself is complex and context-dependent. Explainability refers to the ability to understand and interpret why an AI made a specific decision. Like a doctor explaining their diagnosis reasoning, explainable models provide transparency. This is crucial for high-stakes applications like healthcare and finance, where stakeholders need to trust and validate AI decisions. Adversarial examples are inputs deliberately designed to fool AI models, often with imperceptible perturbations that cause misclassification. Like optical illusions that trick human perception, these exploit model vulnerabilities. Understanding adversarial attacks is critical for AI security, especially in applications like autonomous vehicles or content moderation. Model poisoning is a security attack where malicious data is injected into training datasets to corrupt model behavior. Like poisoning a well to make the water unsafe, attackers contaminate the learning process. This threat is particularly relevant as models increasingly train on web-scraped data, requiring robust data validation and security measures. Differential privacy is a mathematical framework ensuring that AI models can't reveal information about individual data points in their training set. Like analyzing statistics about a city without identifying individuals, it provides privacy guarantees. This enables learning from sensitive data while protecting privacy, crucial for healthcare, finance, and personal data applications. Federated learning trains AI models across decentralized devices without moving data to a central location, keeping data local. Like learning a recipe by combining knowledge from many cooks without sharing their secret ingredients, this preserves privacy. This is essential for privacy-sensitive applications, enabling learning from distributed data sources while protecting confidentiality. AI alignment is the challenge of ensuring AI systems pursue goals that align with human values and intentions, even as they become more capable. Like ensuring a powerful tool is used as intended rather than causing unintended harm, this focuses on goal compatibility. This is one of the most critical challenges in AI safety, especially as systems become more autonomous and powerful. Red teaming involves deliberately trying to break, bypass, or misuse AI systems to discover vulnerabilities before malicious actors do. Like hiring hackers to test security, this proactive testing finds weaknesses. This is essential for robust AI deployment, helping identify safety issues, biases, and failure modes before public release. Hallucination occurs when AI models generate false or nonsensical information confidently, presenting it as fact. Like confidently remembering an event that never happened, the model creates plausible-sounding but incorrect outputs. Understanding and mitigating hallucination is crucial for reliable AI applications, especially in factual domains like healthcare or journalism. Watermarking embeds detectable patterns in AI-generated content that identify it as artificial, like a digital signature. Similar to watermarks on currency, these patterns prove provenance. This is increasingly important for combating misinformation and deepfakes, helping users distinguish AI-generated from human-created content. A model card is documentation that describes an AI model's intended use, training data, performance characteristics, limitations, and ethical considerations. Like a nutrition label on food, it provides transparency about the product. This promotes responsible AI development and deployment, helping users understand appropriate applications and potential risks before implementation. Compute budget refers to the total computational resources, measured in flops, GPU hours, or cost allocated for training or running an AI model. Like a financial budget constraining spending, compute budget limits what's feasible. This is increasingly important as models grow larger, affecting both environmental impact and accessibility, with training costs for large models reaching millions of dollars. Scaling laws are empirical relationships showing how AI model performance improves predictably with increased model size, data, and compute. Like discovering that studying twice as long generally improves test scores by a predictable amount, these laws guide development. Understanding scaling laws helps researchers and companies plan investments, predicting what performance gains are achievable with additional resources. Emergence describes abilities that appear in AI models at certain scales but aren't present in smaller versions, seemingly arising spontaneously. Like how individual water molecules don't flow but large collections create rivers, complex capabilities emerge from scale. This phenomenon is both exciting and concerning, as it means larger models may develop unexpected capabilities both beneficial and potentially problematic that weren't explicitly programmed or anticipated.